Oftentimes, the problems that we're going to be doing in calculus that involve limits are going to be limits that aren't very straightforward, that we're going to have to do some manipulation in some way to evaluate them. So these are going to be the analytic type problems where we have algebraic expressions, and we might do things like factoring and canceling factors. We might have to rationalize a numerator or denominator using conjugates. We might have to use trig identities. So these are all things that we're going to take an expression for a function, and we're going to manipulate that in a way where we can evaluate the limit. We are going to learn a tool later on that makes some of this stuff not really necessary. In particular, the trig identities are not necessarily some people's favorite. I know the Pythagorean identity here is one that a lot of people remember. The variations on that, maybe not so much. These double angle formulas, most people don't have those memorized. Honestly, I don't have those memorized. So you might want to jot these down in your notes so you have them handy when you're doing these problems. But they are not something I expect you to know, to memorize. I would say you should know the Pythagorean identity, especially the sine squared plus cosine squared equals 1. I wrote the second and third Pythagorean identities in a form that essentially what I did is I took the first equation and divided everything by sine squared of theta to get the second one. And I took the first one and divided everything by cosine squared of theta to get that third identity. So they're all equivalent to each other, just different ways of showing it. So I want to go through a few examples and show what we might do to evaluate limits. I'm not going to do this for all of them, but I do want to point out here that if it works to take this value and plug it in for x and get an answer, then that's what we're going to do. So that would be what's called direct substitution. We substitute -1 for x, and we get an expression that we can evaluate. In this problem, if we do that, we get -12 plus 12 on top. We get 1 minus 1 on the bottom, which is 0 over 0, which is indeterminate. And so when we get that indeterminate form, that's when we're going to have to start manipulating things. So what we can do with this one is we can factor. So when I'm showing my work here, I want to keep the limit on there. As a general rule, we should keep the limit on the problem as long as we have x's in the expression, which I'm going to have in this next step. On top, I can factor out a 12x squared, and what's left then is going to be x plus 1. On the bottom, I can factor out an x squared, and what's left is x squared minus 1. And then that's a difference of squares, so I'm going to take that one more step here and do x plus 1. And so x plus 1 times x minus 1. And so keep in mind that in normal circumstances, we wouldn't be allowed to cancel the x plus 1s here, because then we're removing a discontinuity and it turns into a different function. But since we're dealing with a limit that's approaching -1, we know the values of x are not equal to -1, which means we know we're not canceling zeros here. So this turns into this expression. So we get 12x squared on top over x squared times x minus 1 on the bottom. And after doing that canceling, now we can use direct substitution. And we get, now I'm plugging -1 in for x. I no longer need the limit on there because x is not going to be in my expression anymore. So 12 over, it's going to be 1 times -2, which is -6. Next example here, we have an expression that it's a radical expression. If we were to try plugging in -2 for x, we would get 0 over 0. So again, this is a situation where we need to do some manipulating. To do that in this one, I'm going to use the conjugate of the numerator. So I'm going to multiply the top and the bottom by the square root of 3x plus 10 plus 2 over square root of 3x plus 10 plus 2. And we get a new expression here. I'm leaving the limit on. By the way, I do want to point out a slightly different notation here for the limit. Normally we'll write that x approaches some value below the limit, but it can go off to the side as a subscript also. I'm going to do the bottom first. So we have x plus 2 on the bottom times the quantity 3x plus 10 plus 2. And no need to multiply that out. On the top, when we multiply this out, we're going to have the quantity 3x plus 10 minus 2 squared, which is 4. And simplifying the top, keeping the limit on because x is still going to be in the expression. Simplifying the top, we're going to have 3x plus 6. I'm going to factor out a 3, so we get 3 times the quantity x plus 2. And you'll see we have something kind of like in the last problem where we can cancel now the x plus 2's. Again, we can cancel the x plus 2's because we know x isn't equal to negative 2, so we're not canceling zeros. And when we do that, we don't need to rewrite the expression now. This is going to equal 3 over negative 2 goes in for x, so it's going to be the square root of 4 plus 2, which is going to be 3/4. This one, we're going to use those trig identities. And again, there's nothing wrong with going back and looking those up. So I'm going to rewrite this as keep the sine of x on top. On the bottom, sine of 2x is going to be 2 sine of x cosine of x. And then we can cancel. So the sine of x is cancel. Notice that we're canceling zeros if x is equal to 0, but it's just close to 0. So we have 1 left on top. We're going to have 1 over 2 cosine of 0, and cosine of 0 is 1, so we get 1/2. Last example I want to look at here, we're going to use the double angle identity again, this time for cosine. I only put one of them on there, but there's actually a few variations of this that we get by using the Pythagorean identity. So we can replace sine squared with 1 minus cosine squared, or we could replace cosine squared with 1 minus sine squared. And that's what I'm going to do here. So instead of cosine squared, I'm going to have 1 minus sine squared of theta. And I'm doing that because we have sine in the numerator. So I want to get this all in terms of sine, since I can do that. So we have the limit as theta approaches negative pi over 4 of 1 plus 2, square root of 2 sine of theta over, so this is going to be 1 minus 2 sine squared of theta. Now I'm going to factor the denominator here as a difference of squares. This isn't something that might immediately be obvious, but 1 is a square, sine squared is a square, and then we could think of 2 as the square root of 2 squared. So that's going to be, so on top it stays the same. And I knew that we wanted to do that because I know then that we'll get that expression as a factor in the denominator. So it's going to be 1 plus square root of 2 sine of theta times 1 minus square root of 2 sine of theta. So we can cancel these. I should have probably pointed out at the beginning that if we did plug in negative pi over 4 for theta, at the beginning we would get 0 over 0. Obviously we don't want that, so we have to do some manipulating. On top we have 1. On the bottom we have 1 minus square root of 2 sine of theta. And instead of theta, we should put the negative pi over 4. Sine of negative pi over 4 is going to be negative 1 over square root of 2. So we get 1 plus 1 on the bottom, which is going to give us 1/2.